Welcome everyone to our new edition of in Capitole of Software Architectures for LLMs. This is a series where we plan to discuss about different AI topics or data topics. We had a poll ready for today, but I don't know if, well, maybe we can just run it out. Basically, as we're gonna start talking about LLMs, which is the kind of foundation of generative AI, we were wondering if you had any, you ever had a chance of deployed an LLM app in production? So we're gonna run now. Okay, now the poll is running. People can answer. Maybe we can get some results to understand the assistant's knowledge in this area. Okay, well, the poll is running, and since we have lots of content to go through, I think the best thing is to just go directly into the content. So hopefully this is not very dense presentation for you. It will start a bit more simple. I will cover some parts about LLMs or the most foundational parts of it, and then I will start going through the limitations on software architectures. So as Marta said, my name is Ignacio Rodriguez. I'm a tech lead consultant in Capitole. I joined here in March, and yeah, I'm very happy to be here. So yeah, let's go through the agenda. As I mentioned, we're gonna see what's an LLM. We're gonna discuss about limitations and how there's an engineering challenges with this limitation, but how some architectures in software engineering have raised to cope with these limitations. Then we're gonna talk about evaluation and monitoring of these apps. So let's start with it. So in order to understand what's a language model, the best way is to imagine a dictionary. So imagine a dictionary like an English or the Spanish dictionary with 600,000 words. And in this dictionary, you have words from all different contexts of knowledge. And what you could do is you could basically map our number to each of these words. So for instance, the sentence, "Hey, how are you?" can be translated into a series of numbers corresponding to each word. But now, these are just small numbers. At the end of the day, we have a small phrase, and this is just a small representation of that dictionary. But if we try to compute an Excel sheet in which we try to guess based on all the data of internet, what would be the next word that would happen after a specific one, like the word "are"? What you could do is you could create an Excel sheet with all the probabilities of the next word that would come based on this data. After this, you could actually add some context, and since you're adding more words, you could start converging into a specific probability. So for example, if you add "how are" to that phrase, you see that you can get probabilities like "how are you" at 50%, or "how are they" at 30%. And all of this is just a probabilistic model based on all the data in internet. The key takeaway is that the more context or words we have, the better the prediction. Just as humans make more accurate guesses with more words, so does the language model with more numbers. But what happens when you start adding more and more words? How do you compute this? At the end of the day, if you have a vocabulary of 600,000 words, what happens is that you would need to basically compute an Excel sheet with 50,000 rows and columns. So this problem gets increasingly computational extensive. So until now, there was no solution for this. But what happened? In 2017, engineers of Google Research found out a groundbreaking solution for this problem, which is recorded in this paper called "Attention is All You Need." So I'm not gonna go deep inside this solution. I just want all the viewers in this call to whenever they see a transformer, being able to see, oh, okay, so this is a transformer. But this is basically the unit that made the whole large language model and generative AI possible. So how does this work? So imagine that you have the sentence, my dog's name is Ben. He's a big dog with large paws. Ben likes to play fetch with me. If the language model tries to guess the hidden word fetch after play, the context becomes incredibly important. Sorry. If the model only had play as context, it might guess soccer or basketball. These are more common words following play on the internet. But with more context, the model recognizes that Ben is actually a dog, making fetch a more likely prediction. So this is an example that demonstrates how an annotation-based transformer model can actively guess the missing word by considering extensive context and trained on a vast corpus. So a lot of data from internet. So now what happens? And in the previous example, if you have how are, then you're able to compute all these probabilities that we talk about in these Excel sheets, and you're able to create a generative model in which you start adding more words, getting the most probable word, and you start getting how are you, then the most probable could be I, fine, something like this. So basically, this is called an autoregressive model and can continue indefinitely. You can leave the language model continuously generate and it will start talking and talking. So if we feed to these models, or we train these models with, for example, data from books of Don Quixote, it will start understanding how the writer of Don Quixote was putting words together, and then it would be able to guess the next word continuously and generate the books, if not Don Quixote, similar to Don Quixote. So now that we are closer to understanding LLMs, let's go a bit through the limitations. So in the limitations, we've heard that LLMs will destroy humanity, will take all your job. But the thing is that LLMs have a lot of limitations. Many of the architectures that we will see today get around these limitations and capitalize on them to basically provide better output. So what are some of these limitations? I don't know if you guys have experience with working with, for example, ChatGPT, but you may be able to recognize some of these limitations already. For example, one of the main limitations is that they only know the data that they have been trained on. So these actually, if you ask your model some data about the sales inside your company, they won't be able to answer. Also, the context size is limited. You cannot write to the model a lot of words or a big message. Otherwise, it will start losing attention. We will go through this later. It also scales bad. So the more context, the more words you add to the ChatGPT chat, it starts scaling worse. It is less accuracy. It cannot perform well. It is also limited for text perception. So if you ask the LLM to detect certain things in the text corpora that you're passing through the message in the chat, it won't be able sometimes to do all those tasks. And it's also very hard to evaluate because it's not deterministic. So it's not always generating the same output. And of course, it's expensive for high volumes of data, although this is now getting more and more cheaper thanks to open source LLMs such as the one from Meta, which is called the Llama 3.1. I don't know if you guys are familiar with that. But yeah, so we're going to talk about retrieval augmented generation. So in order for this, we're going to talk about lack of knowledge. So as I mentioned, if you ask the LLM to some question related with the gentleman on the top, it won't be able to answer you. But if you ask who's Rafael Nadal, it will be able to provide you some data about it. So LLMs basically are unaware of concepts outside their training set. And when they don't know very well, what they try to do is, they make an assumption, which we have formally denominate this as a hallucination. LLMs, sometimes they feel like ignorant that is very polite. It's someone that is always able to provide you an answer, even though sometimes it's not accurate. And it sounds very well the way they answer. So, and also the problem that we have is that it's difficult to teach LLMs new concepts. So, but if you're able to provide some of this information to the LLM, like for example, some data about myself, Ignacio, then it's able to actually understand or give you an answer. So this is basically what retrieval augmented generation is like. We basically intercalate between the user and the LLM a retrieval information system, or what in Spanish we mainly call motor de búsqueda. For example, Google, it's a retrieval information system, although it's a particular one. But if you are from the development world, then you might know Elasticsearch, for example. So basically, the use cases that you can do with this are very varied. For example, knowledge-based answering. You can also do summarization. So what we're basically doing is we're taking the query of the user, we are transforming it through an embedding model, which is a way to change words into numbers, as we saw in the example at the beginning. And then we're sending it to a vector database, which will try to measure the distance with other documents inside that database, and then provide this information to the LLM, and then the LLM will provide the answer. So basically, this puts the LLM in just a small box in this diagram. This is a very fancy diagram that provides a view, an overview on all the different building blocks. And the LLM, I don't know if you guys can see the cursor, is only this box over here. So we have other boxes, for example, data pipeline, as I mentioned, the embedding model, vector database. So we're going to focus today only in these 4 components, okay? Or no, I'm actually going to cover also logging and validation. But now in this section, we're going to talk only about this one. So for that, I'm going to cover other limitations and then talk about solutions. So another limitation that we talk about is the performance scaling. So what happens is that LLMs, they scale inversely with the prompt size. So the more data that you provide to an LLM, the worse it can perform. So why this happens? Think about it. You have an attention mechanism that imitates human beings, and when human beings, they are pushed to memorize or a lot of information, or take a lot of information and do some action, they won't be able to perform well. So the same thing happens with LLMs. The bigger the context size doesn't mean that they perform better. And actually, there's some LLMs that they have been fine-tuned to be able to ingest more context, and they still underperform the more for when they are tested against big context size. Another thing that happens is bias. This one is a very interesting one. So basically, LLMs are biased towards certain stuff. How do they figure it out? So in the research domain, scientists have figured out a way to test different LLMs between each other. And how they do it via what they call a chatbot arena. In a chatbot arena, basically what happens is that you put 2 LLMs, one against each other, and then users, human beings, can log in and basically ask them to do some tasks or test them in different ways. And what they figured out is that when a LLM is push or instruct to choose between 2 different things, so for example, A and B, it's always biased through the A, to the option number A. But when you ask the LLM to perform 2 different actions, A or B, they will most likely do the second one. And this happens in all LLMs, but they are trying to kind of limit it in the new versions. So you need to take this into account if you want your documents to be actually well processed if you're implementing some kind of LLM app. So basically, in RAG systems, you have different components that you need. You basically have, but the four main ones are a loader or a parser, which is basically some type of tool that takes your PDFs. For example, imagine you have legal documents about certain about your company, and you want to give them accessibility. You need a loader and parsers that take this PDF, transform them into text or text data instead of images, and basically parse this information, process it through a document processing tool, and then store it in a database. Afterwards, you want to index that information in that database, and then have a retrieval algorithm or some specific way to retrieve the most relevant document for your users in particular. So some of the solutions that you could use for loaders and parsers would be Databricks, Airflow. For document processing, same ones. And then for document storage, you could use Azure Cognitive Search, Elasticsearch, as I mentioned. And for retrieval algorithms, you could use LangChain or some other tools. But as I mentioned, there are vector databases. So vector databases have gotten a lot of relevancy in these last years, and it's because it's a very useful tool to provide fast accessibility to information when you have some way of transforming data into vectors. So how does a vector database works? So imagine that you have a three-dimensional space in which you have and this masculinity, royalty, and femininity. And then a new query arrives. You want to measure king, the word king, against these different areas of or dimensions. What will happen is that king will score high for masculinity, high for royalty, but low in femininity. If the query would be queen, for example, it will score high in femininity, low in masculinity, and high in royalty. So basically what we are doing is we are calculating the distance or the cosine distance between different vectors. And vector databases are very good at doing this. The only problem that we have with vector databases is that sometimes you have a specific use cases that in which it won't work very well. And you need additional strategies for this. For example, imagine that you have a knowledge base of vulnerabilities about Windows 10 and Windows 11, but then you want to access these vulnerabilities about these articles that you have in the past from Windows 10. What happens is that if you send a query to this system, some documents of Windows 11 could come up if you don't have your database well designed. But this is an example of how vector databases sometimes cannot be used upfront. You need to actually take into consideration additional tasks, perform data augmentation tasks in your pipelines to actually get more features out of your data so that you can provide better accessibility. So basically, these architectures can basically post-process your retrieved documents and in a way that can really improve your accuracy. Like for example, as I said, this Windows example, you can add a time component to your similarity search or your vector database to avoid this problem of looking into too much into the distance. There is also other components that you can use. You can use relevance reorganization, where you basically ask another large language model, usually a smaller one. So you won't use OpenAI. You would use like a Llama 8 billion parameter model. And basically, you ask this LLM to reorder the documents that you send that you receive from the database of your vector database before they are given to the user. And in this way, the small LLM is able to take into account some specific features of this data, and your user will get more relevant content for them for a specific query. You can also do contextual compression, where you basically take your retrieved documents and you ask the second LLM again to remove irrelevant parts of it, or even self-querying, in which, imagine that you have a big SQL database. You could use an LLM just to send queries, just to take the query of the user, transform it into an SQL query with the SQL syntax, and then ask the query to the database. So now that we finished this part, we're going to talk about orchestration, partial context. So this one is also a very interesting one. We're going to discuss about this building block in the middle specifically, and this one is going to take us to 2012, 2013, when big data was starting to become popular, and the concept of MapReduce will start getting famous. So imagine in the past that you have the book of Harry Potter, and you would like to count the number of words that you have in the book the number of words of Harry and Potter that you have in the book. So before, you had to go through each page and start counting for Harry and Potter. But what happened? That with MapReduce from Hadoop, they basically figured out a way to make this happen. And what they would do is they would separate the book of Harry Potter in different parts. And for each part, you would basically execute a function that will count Harry and Potter parallelly. And then when all of this is done, then it will execute a reduce function that will aggregate all these results, all these small results, into a big one. And since in this time, you would use a collection of computers instead of one computer, you would basically be able to perform the task way faster. So similar concept is being used now for LLMs. So this strategy of splitting data, it's deterministic, and it involves no AI. So basically, what you could do is you could use an LLM, as I mentioned, to do this MapReduce. So if, for example, you want to make a summary of a Harry Potter book, what you could do is you could send pieces of this Harry Potter book into the LLM, and in which you apply a map function that is summary, and then aggregate all this into a bigger summary. So this is basically what a new way of looking at LLMs, and the idea is to basically imitate the way that MapReduce was done in the future. But for this, you need to first define a context chunk to provide to each instance that is going to perform this summary, then provide context chunks to these multiple ones, define a merging strategies for all these pieces of information, and of course, repeat until you finish all of this. The merging algorithm strategy involves splitting the content by any rule of choice, then instructing the model to merge two results into a sensible smaller output. This merging continues until a result that fits your context window is achieved, and this final result will take all the chapters into account equally or thereabouts. So basically, you will be able to create a small summary out of it. But you need to take into account the limitations that we discussed when you're performing these actions and when you are writing down these prompts. There's also the refined documents, in which you basically do this, but in a sequential way. You get the output of the first chunk, then provide it to the second chunk, create a summary, then the third chunk, create a summary, then the fourth chunk, and so on and so forth until you get the end. So there are different ways that you can. And every month, there's a new way of someone figures out a different way to merge this information. So this MapReduce pattern is likely to become a common pattern as the MapReduce was in the 2000s. So there's no restrictions in developing these prompts, as I mentioned, and it will allow us to manually implement better and better procedures to get this information out from the LLM. Um, um, Finally, this is the part that I'm going to talk about LLM evaluation and monitoring. This is a more dense part, but it's an important one. Basically, is the building block here. So the idea is to focus on testing of these apps before they actually go to the user, and then which is the evaluating part, and then monitoring of these apps once the users can use it. So I think it's important to differentiate between LLM evaluation and monitoring. Sorry, in LLM evaluation, we basically compare different models, and then we try to choose the best LLM model that serves the function of the use of that it has to do. So, but evaluating LLMs is challenging and requires a lot of context-aware metrics and measurements, and understanding the tasks that normally the users will take at hand in that moment. So, metrics measures that these metrics should measure the overall intelligence of the LLM for that specific task. So, if, for example, you need to summarize, as I mentioned, books like the Harry Potter, it wouldn't make any sense to define metrics that would take into account, for example, generating poems for a specific use case, for example. So there are many benchmarks in the field for this, but Evals, it's an open source library that is very commonly used in the industry, and it's developed by OpenAI. So it's a good one to start with. So basically, as I show here, the evaluation part is done offline. You take different models, you try different prompt techniques. You even, if you don't have very good results, you start thinking about fine tuning, although it's very expensive. And you do some evaluation, and then what you do is deploy your app. What happens? The difference between evaluations and monitoring is that once you basically have deployed the monitoring, the LLM basically now it's connected and the users can access it. So if you start not having good results with your LLM, the best thing is to do not go into production. Do not let the users start. But once the users are able to go with it, you need to still monitor. But how do you evaluate, or sorry, how do you monitor a black box like a large language model? It's very difficult to do it. So what do? You basically monitor all the components around the LLMs. So you monitor the user's queries, you monitor how the users and the query, but also how the answer of the LLM comes back, which would be the response. And also you can provide some features like user feedback, such as thumbs up, thumbs down, and all of this information should go to a observability platform. So let's go a bit through some metrics that you could use for each of the building blocks. So for example, for user query, you could look at the language distribution, the sentiment score. You could try to classify the queries in different ways. For example, you have a query that provides accessibility to your sales department about sales or in your company. It won't make any sense if you start getting queries about sports or politics. No? So these are the kind of things that give you an understanding of what is happening. You should also be aware of prompt injection, in which it's a vulnerability that could happen, in which someone could inject a small prompt into your LLM and make it execute Python code without your permission. And there's all other metrics that you could figure out. But yeah, so then you have the retrieval augmented generation, so the RAG. And at the end of the day, the RAG is just retrieval engine. So a retrieval engine, we've been dealing with this problem for a lot of time, since before 2000s, and it's just a matter of adjusting the algorithm so that it provides the right information. So what you could do is better your prompts, making sure that the retrieval process, so the information that comes to the user is relevant. But sometimes the most similar information that you have in your LLM is not the most relevant for them. So the core concept is that for instance, we should consider ways to measure if user queries are covered by the vector store. So we can think about ranking metrics to evaluate if the retrieval system is effectively selecting the most relevant chunks. We can even think about using LLMs to score other LLMs. This procedure that it's getting more and more relevant in the industry, although some parts of the industry think that it may not be the best way. Still, this is an area of research. But basically, also what you could do is for model response. For example, the number of refusals that you get from the model. If you get an answer and the user doesn't like it, okay, then you know that if it's asking again the question, it might be a refusal. So you basically try to log that information, and that is feedback that you can use in your monitoring or observability platform to make your app better. You can actually measure the similarity between the question and the answer. Also, you want to be able to detect the personally identifiable information in case someone's personal data is coming through. And then the user feedback, which is the most important one, but it's also the most difficult to collect. So you get explicit feedback, which is information from users that is provided in response to a request by a product. So, for example, thumbs up, thumbs down. Many platforms are providing this kind of feature. Implicit feedback is information we learn from user interactions without needing users to deliberately provide feedback. And as I mentioned before, it is also very common to use for this part of the observability platform to use LLMs to evaluate the user's feedback. So basically, we discussed 4 different phases of monitoring, each of it with its own measurements. This can provide information from different perspectives, and it's very relevant to create metrics specifically for the use case. And there is a bunch of open source libraries that already have developed this kind of observability platforms. How we are with the time? Are we good?
Yes.
Okay, 45. Good. So agent architectures. So finally, this is the last part. Sorry if we've been it's taking long, but basically agent architectures are what actually it's implementation of LLMs apps, different from RAGs, but basically can perform different actions. So for example, you have basically what they do is they decompose a task into smaller tasks. They execute these small tasks and decide when to resort to external tools. And they can also reflect on the results and present them in different ways. It's a very interesting concept. So some of the frameworks that have been developed already for this are chain of thought, which basically you ask the LLM to take a task step by step. There's an additional or kind of an extension of this one in which you ask reasoning, but also act. So you ask a chain of thought or a reasoning, but then figure out, okay, what are the different tasks that needs to be done. So you can, commonly they are split into thought, action, and observation. And additionally, there is this other way of doing it in which you add reflections. You ask the model to not only reason, but also reflect and act, but also reflect on the tasks that have been done. And you can do this in different ways. You can provide a set of heuristics or principles that the model can think about for your specific use case, or you can just let it reflect by its own. Yeah, and basically, LLM agents can also use tools, so they can connect to different APIs like Google. I don't know if you guys have checked when you use ChatGPT now. If you ask ChatGPT to search in internet, it will connect to internet, and so this basically connecting to an plugin. You can also ask ChatGPT to perform code by when you ask it to, for example, count the number of words in this paragraph. It will actually write down a piece of code that will then execute to verify that. So yeah, there's a bunch of tools that you can use for this. So to summarize, although AI is often perceived as super capable and potentially world altering, it still has its own limitations. Every time we break a limitation, we find that integrating AI into real production system is complex, but we have architectures like RAGs that help us design better apps. So in my perspective, 90% of what I see involves RAG orchestration, monitoring, and agents. But yeah, I hope with this presentation, you have more clear view on what RAGs are. And just I would like to provide some reference of what I look for information. I basically based my research on this very important famous architect article called Emerging Architectures for LLMs. And there's a bunch of videos in internet from Google and Spotify, which are also very relevant. And they specifically this one by Gustav Söderström, the CEO of Spotify. But yeah, that's it. Thank you very much.